All right, so we're looking at exercise 10.417, looking at part 1, and just going back and looking at what normal means. So the definition of normal is that, let's just review that, is if for any left coset GH, that's equal to the right coset HG. Another way of saying that, sorry, is that every left coset of H is also a right coset of H. And another way of saying that is if H is normal, if for every G and for every little h, we have GHG inverse is in big H. For every G in big G and every H in big H, we have GHG inverse is in big H. Now, in 10.417, it seems like we're talking about G inverse HG, so that would probably be useful to use this definition for normal instead of the other one. So I'm going to go ahead and use definition 10.413 to do this exercise instead of the original definition. And I can do that because it's already something that's proved in the chapter. So let me go ahead and grab my definition 10.413 and put it here. And it didn't take. Let's see where it is. Don't know what happened to it. Let's try again. Let's try again. Put it down there. Where's my cursor? All right, there's my cursor. Let's go back to screen clipping. I hope this doesn't show up enormous. Oh, good. All right. All right, so that's what I'm going to use. That definition. All right, so we're given that big H is normal. So we'll start with big H is normal. So let's just say that big H is normal. And that's given. And then we want to show little g and big G and little h and little h. I want to show that G inverse little h, G is in big H. Okay. So let's see. Now from the definition here, we have for every little g and every little h in big H, we have little g HG inverse is in H. Now what's the difference between this guy and this guy? Yeah, I am asking you. You're the only game in town. Oh, you should have spoken up earlier. Okay. Right. Well, at least it's on the recording, I suppose. All right. So my question was, we're doing part A here, and we want to show for little g and big G, little h and big H, we want to show that little g inverse H, little g is in big H. Now, this one here says that given any little g and big G and little h and big H, we have GHG inverse is in H. So what's the difference between those two? Yeah, this is what we want to prove, right? Yeah, this is what we want to prove. This is what we get from the definition. Well, yes. Don't they both do what? No. Well, no. I'm not sure what you mean. Both equal H. I'm not sure what that means. This is something. So what I can conclude from this, from the definition, what I can conclude from this is that if I got my G and I've got my H, and if I take any little h in here, and if I take any G out here, any old G out here, then what this tells me, and I can assume this is true, what this tells me is that GHG inverse is in little h. It's in big H, sorry, it's in big H. Now, but I don't know from this, how do what I want to show in part A, what I want to show is that G inverse HG is in big H. This is what I have. This is what I know from the definition. Right? Let's distinguish between what we know and what we want to prove. This is what we know. This is what we have. Right? But how about G inverse HG? So that's the question mark. Where is that? Is that in H or not? Is that in big H or not? That's the question. So what do you think? Wait a minute. There's no coset on this picture. All right. So you're saying that since big H is a normal subgroup, so what you're doing, I mean, what the approach that you're taking is you're not using this definition. You're using the coset definition. So maybe we can go and do it that way instead. We could do it that way. All right, so let's think about that. As an alternative, we could take a look at this. We could say big H is normal, and that tells me that G big H equals big HG. Now, what we want to show, if we have a given G and G and big G, little h and big H. We want to show what? Oh, we want to show that G inverse little h G is in big H. All right, so let's see. So how are you gonna show that? Using this coset fact, how are you going to show this? G inverse. Okay, go ahead. All right, now what, all right, so you're saying that here's my big G, here's my big H here, here's my little h, and you're saying what? You're saying, are you saying G inverse little h is in here? Well, the short answer is no, that's not true. Not in general. If that were true, then there wouldn't ever be any cosets. If G inverse little h was always in the big H, then anytime you multiply something in here by an element of big G, you'd stay in here. So that's not true. But what does this mean? What does it mean that G big H equals big H times G? What does that actually mean? No. Let's go back and look at that. Let's go over some of this stuff. For instance, we had a case where, let's see. Let's go back to here. Go back in the context. Okay. All right, I'll pause and then you can come back. Here. So I flipped to this case here where H is the subgroup of S3. And if you remember, S3 is not abelian. Because of the flips don't commute with the rotations. And here's a subgroup. This subgroup here. Are you still there? Did I lose you? And notice that S3 is not abelian. However, I have this subgroup with 3 elements. 1, 1, 2, 3, 1, 3, 2. That's the group of rotations. And when I computed the left cosets, well, there's two left cosets. There's the same group 1, 1, 2, 3, 1, 2, 1, 3, 2, and then there's this coset here. Now, if I compute the right cosets, I get the same 2 cosets. So you said, so let's go back to our picture. You said that this means that it's abelian, but no, it doesn't mean it's abelian. It just means that if I create this set, if I take big H and I multiply everything on the left by G, I get another set. This set turns out to be the same set as if I take everything in big H and multiply on the right by little g. It's the same set. But it doesn't mean abelian. All right, now what this does mean is, for instance, if I take little h and multiply that by if I take a little g and multiply it by h, and that means that that's going to be a coset here, which I can call gh. And gh does contains g, because it contains g times the identity. It also contains gh. Right. Now, according to this, gh equals hg. So that means that, for instance, hg is also in the set. It's not the same element, but it's in the same set. So it doesn't commute, but it's in the same set. And what that means is that for example, is that here I have this element, little g times little h. Or let me take this one. This element, little h times little g here. What that means is there has to be another h prime such that hg equals h prime g, equals gh prime. Because these cosets are equal, it means any element in this coset here, any element in this coset, big H times G, is also an element in this coset, which is G times H. So there must be some other element, in big H that makes this equality true. All right. So let's see. So I could say that I can say here, since I'll just write that down here. Since since h is normal, I have gh. Stop it. Okay. Gh equals hg. So there exists an h prime. This is an h prime in big H, such that gh prime. Why won't it let me add her to the call? All right, all right, here, I'm gonna do this. Okay, and then I'm gonna add her to the call. So Skype is just a piece of junk. Why is she not showing up? She called me, and then she's not showing up as online. Here, let me call. Okay, here we go. All right, let me. I'm going to call her and put you on hold for a second. Hello? Yeah, there is. But I'm with Jesse, and for some reason it's not letting me, it's not even showing you online. What are you, what device are you on? I'm not sure why it's not showing you online. Well, yes. All right. Well, let me mess around with this. Here, hang on. I'm going to go back to Jesse. Hang on a second. Jesse, you still there? All right. Let me try to add you to hers. All right. Bye. All right, I'm going to try to add Jesse to your call. This thing is a piece of junk. Why won't it let me add? Why won't it let me add him to your call? All right, I'm just going to have to create another call with both of you on. I'll be right there. I'm going to hang up. I'll be right there.